thanks to the break, and I've got the last 17 view graphs here. They just print off. So, continuing in this vein, we're seeing that the neutron multiplicity counters have to have higher efficiency, and less important, but it's nice to have shorter die-away time too. Here's a Pickrell multiplicity counter that was used at Rocky Flats. Again, higher efficiency. And here's that same counter being used for inventory verification at Rocky Flats. Are you familiar with this? And here is the granddaddy of them all. This is the mega counter. This is called the epithermal neutron multiplicity counter. The epithermal moniker is absolutely irrelevant. The only thing that's relevant is the fact that the efficiency is now 65% and the die-away time is 22 microseconds. Compare that to the first case that I showed, which was the high-level neutron coincidence counter. The original efficiency is 17% and the die-away time is 43 microseconds. So the point of it is that this thing now has reduced the die-away time by over a factor, well, about a factor of 2, and the efficiency now is almost 3.5 times as large.
Besides the tube pressure, what reduces die-away time?
Lots of tubes in close packed proximity, so that basically when the neutrons, after they moderate and they start to diffuse, they hit something real fast.
So that's close packed.
Yes, close packed and thick, so the neutrons can't diffuse around here and wander around. They're gone. And so you can see this is what, 4 layers of tubes, and then they can put a center of piece in here and add another couple of layers of tubes.
Why do they use the term epithermal in there?
I have no idea. They like it. It should be called the super high efficiency, super low die-away time neutron multiplicity counter, but that's a mouthful. So epithermal sort of has a better ring to it. Here's a picture of it. Actually, there is a reason for it. Is that they close pack those tubes. It goes back to John's question, not because they close pack those tubes so much and got rid of so much polyethylene that the neutrons are not even fully moderated. They actually started to get to the cusp where they started to even lose moderation, which actually would start to lose efficiency in order to get that close packed results, and they optimized it to get the best measurement results. But that's the real reason. But the significance is high efficiency and low die-away time. All right, let's just, after all of this, how does it do? Here's the pyrochemical neutron multiplicity counting, showing the standard neutron coincidence counter assay versus a multiplicity assay. These are for dirty, that is, impure samples with some multiplication, not too much. We're not seeing too high a mass here, but you can see the red dots show the error. This is assay versus reference, so 1 is perfect, and this is the assay versus reference. And you can see the red dots are coincidence counting, and the blue triangles are multiplicity counting. So it gets rid of the bias, which is the whole point of the exercise. That's a pretty dramatic example. Here's another example for some Lawrence Livermore data. Again, reasonable ranges of mass. Again, assay versus reference value, and you can see the 3-parameter multiplicity versus the conventional 2-parameter coincidence counting. And again, you get rid of the bias error. And here's just some metals versus oxides showing the same kind of thing. Again, getting rid of the errors. And that's for the case. Yeah, what they're showing here, actually, the next 2 slides should be shown together, and that's the way I didn't do it very well. These are for metal and oxides using coincidence counting. The scale here goes to plus or minus 20, and here it is at plus or minus 10, using metals and oxides using multiplicity and multiplication correction again. Here's some that John might be familiar with. This is doing the known alpha versus the multiplicity, where the known alpha is shown in red and the multiplicity is shown in yellow. Again, it's declared over measurement result. So it clearly does a great job in correcting the bias error at the cost of some precision. The bias error due to varying multiplication and unknown alpha, so impure samples. And here's sort of a summary of all that, which is the success rate is defined as within some, whatever standard parameter you want, known alpha versus multiplicity, the rates that you can achieve within some clearly the multiplicity does work. Now, that's not the only issue. I'm going to just bring this up a little bit and say that there are other issues that can affect multiplicity assay. One of them, for example, if you're solving for mass multiplication in alpha, and I alluded to this before, I'm not going to go into details, I'm trying to stick to a sort of central thread, but there's also the possibility of, if you know the multiplication, you can solve for the efficiency, so there's a concern about matrix effects and attenuation. There's also an issue of energy sensitivity, because energy sensitivity per se is not the issue. What it is that energy sensitivity affects efficiency, so there's a variation of efficiency. But the new modern multiplicity counters with their multiple rings actually do a better job of flattening the energy sensitivity and actually reducing the uncertainties due to efficiency. And the reason is this, is that efficiency can be affected by two mechanisms. One cause, two mechanisms. The cause is matrix. The cause is other materials that affect the neutrons, that they collide with the matrix before they get detected. That can do two things. It can reduce the energy or shift the energy of the neutrons, and it can also absorb some of the neutrons so that they're gone. Well, the absorption process affects both multiplicity and coincidence counters equally. Obviously, if you don't see a neutron, you don't see a neutron. But the energy sensitivity is another one, where actually if you change the energy spectrum, if you cool the neutron spectrum because of a few collisions before it gets detected, that it changes the effective efficiency because the detector is designed for a certain energy neutron. If you change that, the efficiency shifts. But because the multiplicity detectors have many, many rings of detectors, they tend to have a much broader and flatter energy sensitivity than do coincidence counters, so that this effect of matrices is actually better for neutron multiplicity counters in addition. All right. Last subject. And this is leading into, this is actually the part that I enjoy the most. This is leading into the second lecture. And in some measures, this part of the discussion is personal for me because it represents my own intellectual struggle of figuring this out. And the first question I had is, when we talked about multiplicity counting, is what is a single, double, or triple? Well, I'll give you the stock answers, and I'll give you why they bother me. From coincidence counting, we know that singles are totals, doubles are reals, and triples are, well, three things at a time. Well, that's great. I sort of have an intuitive sense of that. It still doesn't tell me much. But the thing that really bothered me was this one. The singles, doubles, and triples are the first three factorials of the neutron multiplicity distribution, or more precisely, the detected and counted neutron multiplicity distribution. And I said, well, first thing, what is a multiplicity distribution? The second thing is, what is a factorial moment? And I've answered those two questions already, by the way, in this lecture. The third question is why do we care? And why am I using a factorial moment? Now, in statistics, we don't use a factorial moment. We use a polynomial moment. Why aren't we using the polynomial moments in the neutron multiplicity distribution? Or hell, why not the Fourier moments? That is the Fourier elements and the Fourier transform. Lots of different transforms, lots of different moments. Where did these guys ever dream up factorial moments, and why are we using them? No basis in anything that I could find initially of why we would use singles, doubles, and triples. What's the essential physics?
If doubles are reals, are triples surreal?
No, we have to actually start from the beginning and go in all three. Now remember, the multiplicity distribution, I'm reviewing because this is exactly what we talked about already. The multiplicity distribution is the number of counts in a particular bin, or an event. The event of seeing so many neutrons in a particular time window. I saw 3 neutrons on my shift register. That's an event. I count that as one event with a multiplicity of 3. 50, one event with a multiplicity of 50 and so forth. And we can have a multiplicity distribution in the case of a single nuclear event like a spontaneous fission or induced fission, or even a multiple event, a sequence of events that, if it's causal, occurs on short time scales relative to the detection time, is a short single event. It's actually called a superfission, but it basically means a single event. And we can get the multiplicity distribution of that, meaning the probability of getting 0 through whatever number of neutrons out from that single event. Or we can talk about the detected neutron multiplicity distribution, which is simply the same thing, except that now we're looking at the detected neutrons and counted neutrons from a sample. But other than that, they're the same. And we've shown what those factorial moments are in the sense that we can calculate them as sums, or I like to think of it as integrals over probability distribution times basically the combination formula, which actually starts out as factorials. Remember, it's n factorial divided by n minus k factorial over k factorial. So even though we actually only see a couple of terms here, which isn't a full factorial, because of its genesis in the combination formula, they call it a factorial moment. But I don't care what you call it, these are the moment distributions. Gee, that's nice. Why do you care about this distribution? Why not a polynomial distribution? Why not n p of n squared p of n, n cubed p of n? Why not the Fourier moments? Why not take, this is getting too close, the z transform just like we would in digital signal processing? Why factorial moments? Where do they come from? Because in a sense, this whole discussion and our use of singles, doubles, and triples has been somewhat intuitive and absolutely has had no fundamental basis at all. I said we're talking about singles and doubles and triple correlated events, and why? Why are those things orthogonal, for example? What meaning independent? Why are they independent? Why are they separate pieces of information? Why are you using those things? I wanted to go a little bit into this. There's two reasons for it, actually. One is historical. The real problem was that the Rossi alpha distribution originally came from reactor physics and reactor science, and they had seen these correlations. And the trouble was that they knew mathematically, as we discussed in the coincidence lecture, how you actually figure that out. Remember the rulers and so forth. But the problem was that the incipient work on this was how do you actually do that with a reasonable amount of electronics? How do you actually get correlations with reasonable sizes of electronics? And we didn't have super modern electronics like we do today. These people had just basic 7400 series digital logic. So it was a problem. Now today, we actually wouldn't need to do this. And actually, if we were to start all this today, we might not even develop a lot of this stuff because we have things like the list mode module that counts and tags every incoming event with the time that it arrived, and you can analyze that any way you want. And actually, one of the ways that it's done that is what is known as the Feynman moments, Feynman variance. And that approach actually has some statistical benefits compared to multiplicity. But the point is that when this was originally invented, we didn't have the kind of electronics to do that easily. The second reason is mathematical. And when we talk about the first, second, and third factorial moments of the neutron multiplicity distribution, and we know what a multiplicity distribution is, we know what the factorial moments are, but what I want to do is establish why do we take those factorial moments as opposed to polynomial moments or Fourier moments or pick one. And those factorial moments are a result of the established mathematically the correlation between the point model equations and in fact the physical processes of alpha n emissions, spontaneous emissions, and induced fissions. So the question is, why do they come out and how do they come out? What is the logic? We're going to go back to this issue again. This is the third time I'm going to state this issue in this lecture, and this is key, and it's a key conceptual point, both with coincidence counting and multiplicity counting, and here it is. Remember this diagram from the coincidence lecture. If you have the case of a counter, you have a single fission in that counter, and you have the canonical two neutrons given off by that single fission in that counter, you count both of them at the same time being defined as within the counting window of the detector, the diagram. And you have a second case, somewhat of a Gedanken experiment, where you have two alpha n decays shown here, alpha decay collision with a light nucleus giving you a neutron, both give you a single neutron at a time, and by accident, by coincidence, these two things happen at the same time too. You get two neutrons created at the same time in your detector, which then get counted in your detector window. How do you tell the difference? You can't. And we talked about this before. Extend this to multiplicity. We have multiple kinds of events that we could have here. We could have a single spontaneous fission that gave you three neutrons all at once. Because remember, we have that distribution that can happen. We can get three all at once, or four, or five, or six. Or we can have the case where we have some induced fission, where let's say an alpha n gives off a neutron, which induces a fission neutron. Now you get three neutrons off that way. Or we have a fission that gives us two neutrons and one of them gets absorbed, but one of them induces a fission, and we see 3 neutrons from that as well. Now, those are all singular events where we get 3 neutrons from a single event. Single event because they're causal. Induced fission is caused by the neutron that caused it. Therefore, it's causal. So it's a single event. But there's also the case, in the case of the triples, and this goes back to John's earlier question of how do I tell the difference between one of those single triple producing events and, for example, a spontaneous fission with an alpha n decay, which just happened by accident to occur at the same time, giving me 3 neutrons. Those are 2 very different processes. One is a single event, and one is 2 events that occur accidentally. How do I tell the difference? And the problem is I can't. But what I can do is I can talk about probabilities of what is the probability that I have a single event giving me 3 versus the probability of 2 events giving me 3. And how do I do the mathematics of that? And I'm just going to outline it. This is the basic concept of how these equations are drawn. The probability of measuring a neutron event is a random variable. The probability of measuring the event of 2 neutrons is a random variable. The probability of an event measuring 3 neutrons is a random variable. Let's stick with the triples now. So I have the case of the random variable giving me 3 neutrons by a single event. But I also have the case where I've got 3 neutrons by 2 events. 2 neutrons, let's say, and 1 neutron. And those are random variables, and we add them. We add those random variables. Basic probability. Let's consider how you add random variables. Well, this is really fundamental probability, but I'm going to go actually back to the basics of what is a random variable. And we know what a regular variable is. Let's take a real variable. A real variable is any number between minus infinity and infinity. A random variable is actually 2 pieces of information. It is a variable that can take a number of particular values usually defined in a set. Coin toss can take 2 values, heads and tails, 1 or 0 if you want to do it mathematically. A die, rolling a single die, can take 6 values, 1 through 6, obviously. But coupled with that, the possibility of the set of the possible outcomes, or possible measurements of that random variable, is also coupled with it, and integral to it, is the probability of what each of those outcomes will be. 50-50 in the case of the coin toss, 1 out of 6 for the die. If you roll 2 die, the number of, well, I don't want to go there actually. So the point is that you have a random variable. Now the question is, how do you add random variables? And well, now I'll answer it. Let's say you have 2 die and you want to roll the die. Now the possible outcomes of 2 die, each has one value of 1 to 6, is now 2 to 12. Snake eyes to double sixes. What is the probability now of that distribution? What is the probability distribution of getting snake eyes to boxcars with 2 die? How do you calculate it? Well, we all know how you calculate it. You sit there and because with 2 die, we can run through the probabilities and say, okay, it's 1/6 that it's this, that we get a 1, and it's 1/6 that we get a 1, so it's 1 to 36 for snake eyes or boxcars, and we can count the total number of probabilities. It's a straightforward probability question. But how do you do it in general? How do you actually calculate the new probability in general? And the answer is with a convolution integral. Convolution integral, and we can actually work it out with a die, is the formal mechanism of combining the 2 probability distributions when you're adding the 2 probability variables. Now, convolution integral is an extremely powerful mathematical concept. It is used in electrical engineering, it is used in systems analysis, it is used in digital signal processing. When you want to calculate, for example, the response of an electrical network on a particular signal, you take the response of that electrical network and you convolve it, you run the convolution integral with the signal. Same thing is done with digital signal processing. If you have a digital filter, the digital filter is convolved with the incoming pulse stream. And when you want to add 2 probability variables, you convolve the probability distribution functions. In the second lecture, we're actually going to do that by hand. Therefore, the point model equations, if you were to then derive them from these sort of basic principles, are really the expectation values of the convolution of these various different cases. Okay? I've got a triple. How can I get a triple? Well, I can get a triple from 3 single events convolved with the probability distribution of the event of a double plus a single convolved with the probability of an actual triple event. Those are all separate random variables, and you would convolve them and take the expectation values. The problem is that it's next to impossible to evaluate the convolution integral. Very powerful thing, like so often in mathematics. Convolution integral is great. It says everything you need to say, and it's almost impossible to evaluate. And when you're trying to do something as mathematically or as real-time as this, it's next to impossible to evaluate. Now, what we use to basically evaluate the convolution integral is something called the probability generating function. And what it is interesting. It is analogous to the Laplace transform, and it is identical to the Z transform for the case where you have ones and zeros. By the way, the Z transform is a Laplace transform in discrete time. So the probability generating function is mathematically equivalent to the Z transform, which is mathematically equivalent to the Laplace transform, except that the Laplace transform is in continuous time. And the Z transform and the probability generating function are discrete events. But the property of all three of these things, just the discrete time versus continuous time, is not the significant thing. The properties are the same because the probability generating function, or the Laplace transform, or the Z transform, converts a convolution integral of two functions into their simple product. That is, instead of taking the convolution of two functions in the time domain, I can take the product of those same two functions in as their Z transforms or their Laplace transforms. And multiplication is a lot easier than convolution. I can do multiplication. Most people can do multiplication. Convolution is hard. Multiplication is easy. So when we add, well, let me continue. I'm going to maybe belabor the point. But for example, electrical engineering, if you have a filter, you try to convolve the filter with the input signal to get the output signal. Tough to do. Or you can take the Laplace transform of both, multiply the two, and now you've got the Laplace transform of the output like that, because it's just a multiplication. You take the inverse Laplace transform and you have the answer. Standard technique used in electrical engineering. Same concept here. We're going to take the probability generating functions of these random variables in order to then combine random variables, because it's just the product of the probability generating function gives us the convolutions of those two random variable probability distributions. Same concept. All we're doing is finding a simple way of calculating the convolution integral. And then what happens is that then all those different cases, when I want to add the random variable of the case of the triple and its probability distribution function, which is an honest-to-God triple caused by an event that caused a triple, versus two events caused by, let's say, a double and a single, also adding up to a triple. I need to convolve those probability distribution functions. That's hard. I take the probability generating functions and multiply them. And then I can add them all together. Once I do that, I have a way of expressing the multiplicity equations in terms of these now probability generating functions. Think of Z transforms. The other aspect of the probability generating function that is nice is that the derivative of the probability generating function gives you the first factorial moment of the expectation value of the probability function. There's nothing deeply significant about that. It's just a mathematical result. And the second derivative gives you the second factorial moment, and the third derivative gives you the fourth factorial moment. So once you've done these equations, you can now set up differential equations, and what you get is the expectations of the factorial moment. And so the point is where all this comes from. When you talk about singles, doubles, and triples, which are the first, second, and third factorial moments, is that they are basically the first, second, and third derivatives of the probability generating functions, which are the Z transforms of these probability distributions, because we've got to add random variables. And that is the way we do it. And that is where the equations come from. In the next lecture, we'll actually do it mathematically step by step.
The different way of
derive equation, different way of doing to get a singleton doubles and triples equation from base theory, the PGF.
I'm not sure. Are you saying Bayesian analysis to get the singles, doubles, and triples?
So this way, you mean a different way or new way of
No. This is the standard way it's done, and I'm just trying to explain when you look at the mathematics. For me personally, when I looked at the mathematics the first few times, I didn't understand why the guys in the papers, they just started pulling out probability generating functions and multiplying them together, and I said, well, that's nice. Why? What's the concept? And what I wanted to establish sort of is the conceptual framework for two things. One, this concept of singles, doubles, and triples as correlated events is not arbitrary. Where does it come from? And it basically comes from the mathematics where you need to add random variables. Ultimately, that's where it comes from. So that's one point. And the other point is I wanted to get just a rough outline of the concept of how the mathematics is, because I don't believe that you can do mathematics if you say, all right, here's this step, and we're going to do the following, and here's this step, and then we're going to do the following, and here's this step. Why are you doing those steps? And the point is I wanted to establish the why framework now, and so that you're intuitively comfortable with these ideas when we do it in the next lecture. So that when I do all these steps, you're going to say, okay, I know where he's headed with this.
So will you explain let's proceed to the next lecture?
Yes, we're going to derive it.
Question, we've got neutrons from alpha and neutrons from fission. What about neutrons from delayed neutron precursors? Where do they fit in?
Good point. They come in as singles as well, but they're so small that they're ignored in the point model equations.
Okay, they're just not significant.
They're just simply not included in the equation. It's a good point. It is a correction term. Okay. We're done. Thank you very much.